The NASA Glenn Research Center's Icing Research Tunnel, or IRT, in Cleveland, Ohio, helps NASA and the national and international aviation industry better understand the effects of environmental icing on aircraft, to develop and test ice protection systems, and to verify operation of aircraft components. This tunnel has played a key role in making flying the safest and most reliable method of transportation today, forging its mark on aviation history along the way. With constant renovation and upgrade in the 60 years since it first came online, the IRT has remained a state-of-the-art, world-class facility, helping to solve icing problems for aircraft, from small general aviation to large transport airplanes, rotorcraft, and military aircraft. In these days of planned obsolescence, this grande dame of the world's trailblazing wind tunnels is still providing the cutting edge of aircraft designers with services so valuable that tests must be booked a year in advance. Icing has remained a problem that must be solved for each new aircraft, but in aviation's early years, it was a severe limitation, hampering commercial aviation during the cold months and making direct flights across the North Atlantic almost impossible. Completed in 1944, during the Second World War, the IRT was built to try and solve this significant problem. During the war, American C-46s operated a massive resupply mission for U.S. and Allied troops in Asia. The route ran over the world's highest mountains, the Himalayas, and flew through some of the worst icing conditions encountered by Allied forces. Over 100 planes were lost while crossing this Burma hump from what was then India into China. The planes were lost not to enemy fire, but because of icing. When an aircraft flies through a cloud, the cloud's water droplets can form ice on its airframe. The shape of the ice on the airfoil, and to a lesser extent, the weight of the ice, can all adversely affect the plane's aerodynamics, decreasing lift and increasing drag, causing stall and other control problems. The Air Corps turned to the National Advisory Committee for Aeronautics, as NASA was then known, for help, and the IRT was conceived. The Icing Research Tunnel simulates the icing conditions found in nature. For the aircraft component or model, being mounted in the IRT's test section is like flying through a cloud. The high wind speed, very cold temperatures, and spray of tiny water droplets allow researchers to study icing on aircraft surfaces safely and economically. The wind in the IRT comes from a 25-foot fan, which can turn faster than 7.5 times per second. The fan's 12 wooden blades are made of laminated Sitka spruce. A 5,000 horsepower electric motor turns the fan with precise control and regulates airspeed. Within the test section, the airspeed can be varied from 25 to about 350 miles per hour at a sea level pressure. Turning vanes direct the flow of air produced by the fan into the cooler or heat exchanger. As the wind flows through the heat exchanger, the air is chilled. The total air temperature can be varied from about 40 degrees Fahrenheit to minus 25 degrees Fahrenheit, summer or winter. The 1,800-ton heat exchanger, one of the biggest in the world, provides enough low-temperature air to cool 900 homes. A second set of turning vanes directs the flow of cooled air on through the heart of the IRT, the spray bars. Nozzles in the 10 horizontal bars spray droplets of water about the size of a grain of pollen into the moving air. In spite of the IRT's cold temperatures, the water droplets remain liquid or supercool as the wind propels them toward the tunnel's test section. Behaving like the droplets of water in a cloud as an aircraft flies through it, they instantly freeze when they strike the surface of the cold aircraft component or model being tested in the tunnel. Droplet size within a real cloud varies. Depending on weather conditions, they can range from about 10 microns to 300 microns, or even larger in the case of freezing rain. Droplets from the IRT spray bars can be from 10 to 200 microns in size. They simulate both the size and the distribution of droplets found in natural icing conditions. Each spray position has two interchangeable, different size nozzles, which can be calibrated to the cloud formations found in real weather patterns. What is more amazing, this can be accomplished on the fly or remotely with a touch on a computer keyboard, eliminating the need to open the tunnel and interrupt a test. It's almost as if an aircraft is flying through one type of cloud and into another. The tunnel's airspeed, temperature control, and icing spray system are designed to create an in-flight weather event in the IRT's 6-foot high by 9-foot wide and 20-foot long test section. Articles are prepared for testing in the IRT shop, then placed in the tunnel through a wall or ceiling hatch. Here, the aircraft component or model is mounted on a turntable, which can be rotated to simulate an airfoil's angle of attack as it climbs through a cloud. Ice accretes on the test article's leading edge. Two sets of turning vanes at the end of this section trap and keep loose ice from re-entering the test section as they direct the airflow back into the fan. The control rooms alongside the test section are equipped with computers that regulate the tunnel's various functions. Data can also be acquired electronically, but the IRT depends on visual imaging to collect its most important data. Acrylic panels in the test section ceiling and windows in the tunnel walls, heated to prevent fogging, allow researchers to observe the ice buildup on the model. Tests can be documented by tracing ice shapes onto cardboard, by making molds and castings, through 2D or 3D scanning, and with various types of photography, which include digital and film-based still imaging, video and high-speed motion pictures, infrared thermography, and three-dimensional still images. The tunnel serves a diverse group of scientists from NASA, academia, engine manufacturers, and the Department of Defense. Researchers conduct various types of work here. Basic research to better understand icing physics and ice formation, testing and development of ice removal and ice prevention systems, study of aerodynamic effects of ice and how to prevent hazardous operations in icing, improvements to design and certification computational tools, and FAA certification of aircraft components under icing conditions. The IRT saves the aviation industry millions of dollars by making extensive in-flight tests unnecessary, but it is only one part of the icing story. Increasingly, computer models are being used to predict icing. Codes such as the NASA Glenn-developed Blue Ice can fine-tune their accuracy by comparing computer models to the real-world icing conditions found in the IRT. NASA Glenn's icing research aircraft provides another component of the icing story by testing how ice buildup and ice prevention and removal systems affect flight performance in natural icing conditions found over the Great Lakes. Recommendations based on this icing research are passed on to pilots of commercial aircraft who routinely fly in icing conditions during many months of the year. The IRT has played a major role in developing, testing, and certifying ice prevention methods on gas turbine-powered aircraft. The de-icing systems used on today's jets were also developed here, and the work continues. With today's increased emphasis on saving time, costs, and energy, more regional flights than ever are being flown by smaller, more fuel-efficient turboprop aircraft over shorter distances and at lower altitudes more susceptible to icing conditions. These aircraft use an extremely reliable pneumatic boot system, where a rubber boot inflates and breaks accreted ice away from the leading edge of a wing or tail, maintaining the airplane's performance and handling design characteristics. Other types of anti-icing systems tested in the IRT include bleed air systems and electro-expulsive systems. The IRT is a valuable research tool which can simulate icing conditions in a controlled and repeatable manner within a safe test environment. it continues to provide significant research information towards NASA's aviation safety goal of reducing the number of aircraft accidents. Each new type of aircraft brings with it fresh concerns about icing. NASA Glen's Icing Research Tunnel continues to play a key role in investigating those concerns and in ensuring aviation safety for us all.